Hello everyone. In this video, we will continue to examine topic 4.4, wave behavior, the phenomenon of refraction, and we will introduce the idea of Snell's law. So, as discussed before, refraction occurs when a wave transitions in media, going from a fast medium to a slow medium or vice versa. This wave bends at the medium, and empirically, the velocities of the wave in the media are related to the angles at which they refract. So v1 over v2 equals sine of theta 1 over sine of theta 2. For light in particular, though, we define something else. We define the index of refraction n of the material. And the index of refraction is defined to be the ratio of the speed of light in a vacuum to the speed of light in the medium itself. Refraction is due to the fact that waves slow down. Somewhat surprisingly, perhaps, light slows down in other media. So light slows down in water and in glass and in virtually any transparent medium. And so the speed of light that we think of as 3 times 10 to the 8th meters per second is strictly speaking the speed of light in a vacuum. And that speed slows down significantly when that light is in a material, up to 20 to 50% in common materials like water and glass and plastic. The index of refraction in some ways is sort of redundant with this idea of the velocity because it just gives that ratio of the velocity to the velocity of light in a vacuum. But it is sort of the common way of describing refraction. So, for example, if you have a material of index of refraction 1.4, that tells you right off the bat that the speed of light in a vacuum is 1.4 times the speed of light in that particular medium. So it's just a different way of talking about the speeds and ascribing that speed to the material itself. With this definition of the index of refraction, though, we can define what is traditionally known as Snell's law. And Snell's law simply extends the empirical relationship from before, and it says that n2 over n1, which is equal to v1 over v2, notice the algebra there. If you just take n2 over n1, then n for a particular material, n1 will be equal to c over v1, and simply divide those, then you invert the ratios of the velocities. So n2 over n1 is then equal to sine theta 1 over sine theta 2. This is known as Snell's law and is given in the data booklet, and it relates the index of refraction of both materials to the sine of the angle that the wave represented by the ray makes with the normal in both media. As a result, we can define a particular index of refraction as not just the index of refraction relative to light, but the index of refraction in between any two media. So, for example, this might be a situation where light is going from water into glass rather than from glass into air or glass into a vacuum. I should pause there and note that air has an index of refraction very, very, very close to 1. So the speed of light in air is very close to the speed of light in a vacuum. And I will often refer to air as if the index of refraction is exactly 1. So with that idea in mind, if light is traveling from a material like glass to a material like water or vice versa, then we can just directly define the index of refraction between those two media. Notice this is for those two media specifically to be the ratio of the speeds in those media. So v1 to v2 is equal to sine of theta 1 over sine of theta 2. So, what happens if the wave goes from a slow medium to a fast one? Well, we can extend this idea, apply Snell's law, and we can see that the ray bends outwards from the normal rather than into the normal and we simply apply Snell's law for the two materials, um, material 1 and material 2, in order to find the relationship between those angles. And you'll see several examples of that, both in the homework and in the notes here. Notice here are some typical indices of refraction. You'll see one of the things that makes diamond particularly valuable is that the index of refraction is so high. This keeps sort of light bent and bouncing inside the diamond, which is part of what gives diamond its characteristic brilliant properties. So consider for a second which properties change at that boundary. This is an important concept. Well, as we saw, the velocity changes at the boundary. Why? Because that velocity of the wave and the velocity of the wave in general depends on the medium. It depends on what the wave is in. So the velocity changes at the boundary. Consider too for a second, though. The frequency doesn't change at the boundary because the frequency is fundamentally dependent on the source. Recall that the frequency is sort of how often those waves hit. And you can see in the diagram here, right, that how often the waves hit the boundary can't possibly depend on how fast those waves are moving. They fundamentally depend on the original source of the vibration. So whatever causes the ripple, all right, the ripples will then hit the boundary at the same rate. So the frequency stays the same. But if the velocity changes and the frequency stays the same, then the wavelength has to change as well. And that is in fact what we see in these diagrams. If the wave is going from slow to fast, that wavelength increases. If the wave is going from fast to slow, then that wavelength will decrease. And it's important to sort of understand these. These are all related to fundamentally what these properties depend on, right? The velocity depends on the medium. The frequency depends on the source, and therefore isn't going to change when it hits that new medium. And the wavelength depends on the relationship between them, which means that if the velocity changes and the frequency does not, then the wavelength will be proportional to the velocity. If the velocity is twice as fast, the wavelength will be twice as large, and so on and so forth.